So hello everyone, good morning. Welcome to day 2 of our algorithms, machine learning for algorithms workshop. Okay, I should get it right. And our first speaker will be Professor Anupam Gupta from NYU, who will tell us about online algorithms using samples.
Awesome. Thanks, Piotr. Thanks to the organizers for inviting me. It's almost like this. The workshop couldn't. The title of the workshop couldn't have fit more the title, the content of my talk. So hopefully you'll see what I mean. So I'm going to talk a little bit about some work that we've been doing on this area called online algorithms with a sample. And it's really like using a lot of machine learning type techniques and also machine learning type thinking plus algorithmic thinking to solve some algorithms problems that we want to solve. Okay. So, analysis of algorithms, I'll skip over this this slide very quickly. Beyond worst case, we are trying to go beyond the worst case. We are trying to use learning ideas, both, predictions and otherwise. So I'll start with online algorithms, which most of you probably know. Requests come over time. And as requests come in, you got to satisfy them, whatever satisfy means for the particular problem at hand. And there's a certain cost. And in this talk, I'm going to talk about a certain notion of costs, and you want to minimize the costs. And what you want to do, and I don't know if you guys can actually read it from the back. I'm sorry. Yeah, gosh. So it says competitive ratio out there. So the competitive ratio of an algorithm, yeah. Uh, yeah, sorry guys. There'll be a little bit of this. But tell me when you can't see something. Yeah. Anyways, the competitive ratio of an algorithm is how well your algorithm does divided by how well the best algorithm or the best solution could have been. Right? And you're looking at the ratio and you're looking at the worst case. And it's really a very worst case notion, and it's designed to be robust. Okay. Uh, in today's talk, we're going to still sort of do worst case analysis, but we're going to do this with under a certain model where you get a little bit of extra information on the side. So one canonical, thank you. One canonical problem that I'll talk about, in fact, this is essentially the only problem I'll talk about with slight extension on the next one, is online load balancing. There's a bunch of machines, these boxes out here, and there's a bunch of jobs. And these jobs are these green dots. Oh, wow, nice. Yeah, it'll feel like a movie after a little while. Popcorn, you can fall asleep. Good. So there are a bunch of machines, and there's a bunch of jobs. Each job can only go on some subset of machines. Okay. So when the job arrives, you got to send it to one of the machines. You don't know the future. So the next job that arrives, you got to make a decision for this job without knowing the future again, but of course, knowing the past and knowing all the decisions you've made in the past. And now a third job arrives, and you see, actually, what were we trying to do? We were trying to minimize the load of any machine. So low load is good. And here, suddenly, the load is 2, whereas if you look back, there's a perfect matching from the jobs to the machines. So the optimal load is 1. So remember this ratio between the performance of your algorithm and the performance of the best algorithm, it's at least 2. Fair enough? Good. Okay. Nothing, no rocket science so far. Okay. Online packing covering is another set of problems that I'll talk about briefly. And here there are M resources. So really what you should think of is there's M-dimensional matrices P and C. So M rows and some number of columns. And you got to choose the X's. So that's like choosing, some fraction of each row and summing them up. And they should satisfy some packing covering constraints and some covering constraints. The solution should simultaneously satisfy some requirements which are given by the packing constraints, by the covering constraints, and use some resources which are satisfied by the packing constraints. Okay? And one special case is when these decisions that are being captured, each request can be satisfied using any of one of k actions. So what you're going to do is whenever a request comes in, you're going to choose one action which is encoded in this X vector. And there'll be a corresponding column from the P matrix that will be chosen and a corresponding column from the C matrix that will be chosen. And can I? Absolutely. There you go. Okay. And you don't even have to read all the stuff on the right. You all know what a LP is. We're just trying to solve that LP. But what's happening out here is that the columns are arriving over time. Okay, good. And this is the problem that's also been studied in the past, and people have been interested in this in online settings. And that's exactly what, these are two kinds of problems that we're trying to capture. And if you're bored, you can try to think about how you can capture the load balancing problem as some kind of packing covering. Your packing will be how much capacity you're going to use, the max load, and the covering will be that every job should go to at least one machine. Okay. So at a high level, this is what's happening, and this has been taken from another talk, so you can ignore the first row of this thing. Ignore this thing. Okay. So what am I interested in? I'm interested in how well we can do online. In the offline problem, the last two rows show, the problem that I stated, load balancing, you can solve exactly. It was really a matching problem. If you knew all the jobs in machines and all jobs at size 1, it's really a matching problem. Okay? And for covering programs, you can get pretty good approximations, assuming the right-hand sides are large enough. And how do you do this? The one-sentence description is solve the LP and do randomized rounding, but be a little more careful. Catch me later, I can tell you more about it. Okay. In the online setting, you pay a lot more. And for all these problems, you pay, logarithmic at least. So there's this price of uncertainty. And in order to combat this price of uncertainty, there's this model called, online with a sample. And it's, essentially it came out of several people thinking about, machine learned predictions and, where do these predictions come from? And one thing you could say is, oh, these predictions are IID from some distribution. This is a very natural thing. It's like PAC. We've been doing this for 40 years now. Or this model. So let me tell you the model. And this is the first thing that, just make sure that you understand. It's a perfectly, both are perfectly reasonable things to do. I'm just, suggesting one way to look at it. It's called online with a sample. The process proceeds as follows. The adversary fixes an input. You get to see a sample of this input. P is a parameter, and think of P as 1%. So you get to see 1% of this entire input. Given this, you can learn whatever you want to learn. Okay? And then the actual input will be given to you, and you have to make the decisions online. But as, for the 99% you haven't seen, you still have to make the decisions online. It's a random sample. So just think of each one as being, chosen with probability P. The input is, the way I think about this is that these are all closed boxes, and each box I'm going to open with probability P, and I'm just going to show it to you. And then once I've shown you this, you can think about it. You can come up with an algorithm which is based on this data. And now I'm going to open up the boxes, the remaining boxes, or in fact, all the boxes from left to right. And you're going to be taking decisions as you go along. So part one, I'm not going to talk about for the rest of the talk. This is just to set up context. So answer one is just for context. I'm not going to talk about PAC. No. So, I'm not talking about it. Let's talk about it offline. How about that? I'm just going to talk about answer two, online with a sample. The adversary fixes an online instance. I get to see a little bit of it. Okay, let me see if I, oh, by the way, so it's just some history. I learned about it from a paper of Kaplan, Nauri, and Raz. And then, at that time, we already realized that there was this older paper of Azar, Kleinberg, and Weinberg. But then, a little more digging, and you realize nothing's new, right? Chances are, Gauss was thinking about this thing. But there's a paper of Campbell and Samuels from 81 in optional stopping. They were interested in exactly the same problem. If you heard about profit inequalities, this is the group of people who were doing profit inequalities. And they were looking at all these models back then. Okay, good. So, and here's one way I've been sort of thinking about this. The sample is training data. The input is adversarial. The sample is training data. I get to see it, and I'm going to learn a good strategy from this. And now I'm going to use it on the test data. And I want to just understand that whether there's a strategy, and this is stuff that you learn in Avram and Nina's machine learning theory class, right? Is generalization. You learned on the sort of training data, does it generalize to the test data or not? Try on. Yeah. The input data is ordered. The sample, I'm leaving it intentionally vague. If you want, you'll see the ordered thing. If you want, you see the unordered thing. Whatever works for you. For me, it's not going to be important that you see the ordered thing, but I can totally imagine for other problems, the ordering is important. You choose. To some extent, we are defining the model. We should figure out what the right model is. Yeah. Yes, I'm doing an expectation over the distribution of the p samples, but not over the choice of the input itself. That's adversarial. Excellent. Other questions, please? We good? Model clear? We happy? Good. That's a good start. Okay, so here's what I can tell you. For these two problems that I talked about, what can I do? So for both, the answer is going to be very similar. What I'm going to show you is that I can get a 1 plus epsilon approximation as long as the optimal load is large enough. And I'll try to make this a little more precise. But in some sense, I need the optimal load to be large enough so that there's some signal that I can measure, at least using my techniques. They're very similar results. And let me go over this. And this comes from two papers, and I'll just put in the thing. There's one pretty old paper by now with my students CJ Argue, undergrad Chris Seiler, and my colleague Alan Frieze at the time, and a more recent paper sort of this year with Marco Molinaro on packing covering problems. Slightly different ideas, but there's a sort of a theme which goes through both of these, and which is that just like I learned learning from Avram when I first started, I learned a little bit of parallel algorithms of Gary Miller and Guy Blalock, and it's useful to know these things sometimes. Okay, so with that teaser, let me move on. I'm going to talk about load balancing for much of the talk, and in fact, Piotr, keep me honest and let me know. 40 minutes, right? 40. Yeah, 40. Yeah, okay. So, yeah, oh no, I'm okay. It's a sneaky idea, Nina. I see what you're doing out there, right there. Kevin will kill me. It's okay. Load balancing. You remember the problem. Bunch of jobs arrive. I'm assuming that the jobs have unit size. You can make this a little more general, but using the techniques of the first part, you can't make it much. I don't know how to make it much more general. Okay, good. So jobs arrive, and you're making decisions. The load of a machine is the number of jobs assigned to it in this case, and the make span is the maximum load. You're minimizing the make span. As we said, offline, this is a matching problem, or reducible to matching flows, whatever. Okay, here's the I'll just state these two facts. This is not very important. Greedy is a log m competitive algorithm, and that's the best you can do. And I'll just tell you kind of the log m competitive, the idea for the log m competitive. It's like, a maximal matching is within a constant of the maximum matching. So imagine the following thought experiment, that you were given all the jobs and you just found a maximal matching from the jobs to the machines, ripped out these jobs, found a maximal matching again and repeated. Each time you're matching about half the jobs. So you'll take about log many rounds. Now you just need to figure out how to cast this as an online thing. And it's not a standard proof, but again, catch me. Whatever, if you want something which is slightly off topic, catch me later on. I'll tell you about it. If it's on topic, please ask. It's much more fun to have an interactive thing. Okay, the log m lower bound is actually very easy to say. So let me just say it. The first few jobs that come look like this. What are you going to do? Let's say I chose the top machines. And I'll say, you made a mistake, my friend. You should have chosen the bottom machines. Because I'm going to give you jobs now only on the top machines. And you see the pattern, right? This is exactly what's going to happen. And it's going to give you a log. And there are other examples that show log as well. But, you get the idea. Log lower bound, log upper bound, we've solved the problem in the worst case model. And so the question that we're going to ask is, yeah. So right now, I've just shown you for deterministic, but you can also get something against the value. You lose a constant, but at least in the lower bound, we lose a constant, but yeah, that's all. Yeah. And by the way, there are many interesting questions about like random order and things like that. She has a very nice paper, things like this. But yeah, today, load balancing with the sample, right? Okay, so here's the result I can show. I can get 1 plus epsilon times opt plus some garbage term, which depends like log of the number of machines, and inversely polynomial in epsilon, the accuracy parameter, and p, the sampling rate. Okay? And if you're trying to figure out what happens if p is, you're taking p to the limit where p is like 1 over n, this is not a very good result. So you should really think about this when p is like a constant. Okay? And maybe I'll say one more thing. Avram looks a little worried, so let me just say the next line, and then we'll talk. We'll ask Avram what his concern is. If I just try to use something like uniform convergence, combined with some of the ideas that I'm going to use, and those of you who, uniform convergence doesn't ring a bell, it's just your union bounding over a whole bunch of hypotheses. If you just use that, you can get similar trade-offs. I mean, you can get trade-offs again, but now the trade-offs are much worse. You're polynomial in the number of machines. So the point of this talk is going to be to somehow say that, look, using an interesting mix of learning ideas and algorithmic ideas, you can actually get good generalization bounds for algorithms problems. Machine learning for algorithms, right? Yeah. So that's the general idea. Avram, you had a question.
Do you know if it's possible to do better when opt is not hard?
Good. So I was thinking about this, and I don't remember exactly what results we had. So I don't think I think we had examples showing that a constant is not possible. But, they were very poor bounds that way. Yeah. It's, yeah, you could kind of hide bad examples, and it somehow wasn't working out. Just repeat the same instance many times. Yeah, I mean, that's one way of, I guess, getting it right there. Though, of course, if the sample is like 1% of the data. So you got to, it's not as simple as, because if you want to not see one piece, that piece has to be really tiny, like a constant size. And then it's not interesting. But yeah, I'll try to pin down the lower bounds after. It's been some time. Other questions about this? But just wanted to give you a general sense of what the results are going to be. Okay, good. So we are explicitly learning a good strategy from samples, and this kind of result is not possible with worst case arrivals, clearly. Okay, so there are going to be 3 algorithmic ideas out here that you should take away from, or you could take away from this thing. And the first one is, if opt is large, then finding an integer assignment and finding a fractional assignment are similar problems. Why? Find a fractional assignment, do randomized rounding. A Chernoff bound says that the expected, if a job is going 0.3 there and 0.7 there, send it 30% of the chance over there and 70% there. Every load is going to concentrate around its mean. And here, the opt is large, it's like log of the number of machines. And then Bill can tell us, how to do use Chernoff bounds out here. And then, log of the, if the load is like logarithmic, you get 1 plus minus epsilon approximations for each machine, union bounding. Beautiful. Okay? So I'm just going to find fractional assignments. When a job comes in, I can send it fractionally. And to answer a question that you might be thinking, is this making the problem much easier already? No. There are lower bounds, log lower bounds in the worst case model, even for fractional assignments. Okay? Good. Yeah, I should have mentioned, when opt is large, it does not make the lower bounds in the worst case model go away. Okay? I think my congressperson is trying to call me, but yeah. Is it Tuesday? Yeah, it must be. There's elections. Anyways, good. Okay. So the second one is the kind of the first interesting nugget. The Chernoff bounds are interesting, but we know them kind of. They're old friends. Here's a new friend. There exist what I'll call machine weights. Weights are different from loads, so do not be confused, please. Okay? There exist machine weights so that proportional assignment with respect to these weights is very good. Okay, what do I mean? For every machine, I'm going to write down a weight. When a job comes in, it can go to these 3 machines whose weights are 1, 2, and 4 in this case. It'll send 1/7 to the first machine, 2/7 to the second machine, 4/7 to the third machine. Proportional assignment. Okay? My claim is there exist these weights so that offline, if you knew the entire instance, if you had to ask God, please tell me, how should I assign? God could give you these weights and then you would just do proportional assignment. Okay. So let's just prove this. And this is a sort of this is an idea that's, okay, we'll prove this in a second. Theorem 3. I'm going to use my sample to find these weights. It seems like a clean enough idea, right? So let me tell you how do you compute these weights? So what am I trying to do? I'm trying to show you how to compute these weights, right? That there exist these weights. Okay. For this, I'll use the entire instance just to show you the existence of these. The proportional assignment of, for each job, you're doing proportional assignment for that job, but you're going to look at the load on the entire instance. Okay? So how do you do this? Well, how do you do assignment? The way you do assignment is you solve this LP, which you guys can vaguely see. You can see it? Okay. You're assigning every job to a full extent, to extent 1. Let's say you know opt. Make your life easy. We can talk about what if you don't know opt. Okay? And the load on each machine should be no more than opt, and Xij should be non-negative. Fair enough? If you solve this, any solution to this is going to give you a fractional solution that you wanted. Which solution do we want? Well, we want the solution that has maximum entropy. And this is where, if you haven't seen this before, this comes as, a little bit out of left field. Why maximum entropy? Well, actually, it has, in this case, we choose it because it has nice properties. Okay? And, okay. So we want to understand what this convex program will compute. How do you understand what the convex program computes? You write down the optimality conditions. You write down the Lagrangian. You're just, relaxing every constraint. And once you write down the Lagrangian, you're going to write down the KKT conditions. You're going to take partial derivatives. You've done all this before. I don't have to tell you, but I'm just reminding you, right? And at optimality, you can write down what the conditions are, and the optimality conditions say whatever beast this is. But I'll just reparameterize it. saying xij is theta I. The amount to which job j goes to machine I is proportional to theta I, normalized by the sum of all the thetas that job j can see. Is proportional assignment. So if you solved this convex program, the solution to this convex program, the duals of that, are going to give you precisely these weights that we've been waiting for. Beautiful. By the way, this comes from, there should be a, it's just off the slide. This comes from a paper of Shipra Agarwal, Wahab Merokhni, and Mortaza Zadi Muqaddam. Okay, good. So, oh, thank you. It's a miracle. You should be there for all my talks. Thank you. Good, perfect. Oops, sorry, I got carried away. Okay, so if you knew these things, oh, by the way, where did the epsilon come from? And this is just a technical condition. It's because, if you want, convex programs, no strong duality, right? You need something called Slater's condition, or it suffices to have something called Slater's condition. For that, you need a strictly interior point. You need a little bit of breathing room, some details. Okay. So if we knew the instance, we could find these weights. Okay. Good. Fair enough. How do you compute the weights? So of course, here's one thing you could do. On the sample, run this convex program and you'll get weights. Use these weights on the test data. Again, this is a generalization question we're asking. I do not know how to answer this generalization question either positively or negatively. If you can, please do. Please tell me. Put me out of my misery. Okay? This is a very reasonable algorithm. I do not know whether it's good or bad, theoretically. What I will do is I'll give you a way to find good weights. I'm not talking about the optimal weights, just some good weights, which will give you low load. And I'll do this using the samples. Okay? So I have about 8 minutes left. So let me give you a general sense of how I'm going to do it. So on the remaining, so using the sample, I've found the weights, or found some weights which are good. And now on the rest, I do proportional assignment. Yeah, on these, the weights that I've computed. Beautiful. Yeah, sorry, I'm saying beautiful even though it's my own algorithm. But yeah, thank you. So not after the sample. No, the rest of the thing comes in an adversarial order. And this is part of the sort of trouble. If the whole thing came in random order, I know other algorithms which will do the job. Okay. So here's let me give you the high level idea of how to do this. So first, let me tell you how to compute some good weights, not using the convex program, offline, where you know the entire instance. And then I'll tell you how to do it online. And I have to do this all in about 6 minutes, so we'll see how. Okay, suppose we had the entire instance. What am I going to do? I'm going to use my favorite algorithm. I'm going to use multiplicative weights. I'm going to start off with all machine weights being 1, compute loads based on the weights. If there exist machines which are overloaded, reduce their weights. It's the time and tried and tested approach. Fair enough? Is the algorithm clear? Good. And then repeat. That's it, right? Okay. Multiplicative weights. Almost the sort of naive brain dead algorithm. Amazing brain dead algorithm. Okay. By the way, note that I'm just guaranteeing good load. I'm not saying that this is a good solution. This is like a near optimal solution. It's not a point-wise. It is a good solution to the convex program, but it's not a point-wise close to the optimal. It's just got a good solution value. Okay. What's the So the first question you should ask is, does this terminate? And the answer is yes. There's a very cute analysis, as all these multiplicative weight analyses tend to be. The second question I'm going to ask, and this is non-standard a little bit. Oh, by the way, so whenever I am updating weights, I'm updating all the machine weights which are overloaded. So if there's 72 machines that are overloaded, all of them will reduce their weights. Gosh. Okay. How many rounds will I use? I'll use some polylog many rounds. Okay? Good. And then finally, the sort of elephant in the room is, but I gave you an offline algorithm, another crummy offline algorithm to solve this problem. Right? I need to know the entire instance. Okay. And the whole idea is use samples. To run this algorithm, what do I need to do? If you give me weights, I have to tell you which machines are overloaded. Use the sample that I have to estimate those loads. Figure out which ones are overloaded, reduce their weights, repeat. Okay? Why did I care about the number of rounds? Well, I have a sample. I estimated the weights according to the loads according to those samples. I updated the thing, the weights. Now these things are correlated. I need fresh samples. So here's what I'm going to do. I'm going to take my sample, I'm going to break it up into some number of chunks. I'm going to use the first chunk for the first round, second chunk for the second round, and so on. Now I don't have to worry about it. I mean, there's some negative correlation, but that's only, that's okay. That's good for us. And you can get around that as well. It's not a big deal, right? And that's the whole thing. That's pretty much what I want to tell you. That, if you do this and you can go back and you can try to do this, okay, it requires a little bit of work to show that the number of rounds is small, but you can show the number of rounds is small. And that's really the real idea is lurking. The third one is the conceptual idea that a parallel algorithm can give you good low sampling algorithms. Okay, I'm going to ignore all this. My eyes are bigger than my stomach. And I'll just tell you a little bit about some recent work that we did with Marco Molinaro, where, here is a cartoon of a parallel algorithm. And the parallel algorithm consists of local rounds where the local machines are doing something, and global rounds where we are synchronizing. And we can call these sample robust if the global computation that I need to do can be implemented using a sampling of the agents. And if you can do this, and if you have a low round algorithm, then you can again get an algorithm which is good with samples. It's a similar, that's a philosophy from the first paper, right? But implementing this for packing covering problems, and I'm going to just, say, there's a paper due to Neil Young. It's a beautiful paper, which solves packing covering problems in exactly this thing, in this kind of setup. What we needed to show was that it was robust to taking samples. And that's what we showed. And we abstracted out the whole thing. So if you have a good parallel algorithm, you can get good algorithms with samples. Unfortunately, the only two examples I know currently are packing covering and load balancing. So it's, I don't know how to generalize yet, but I think this idea should be useful. It has to be sample robust, basically. Okay. So just basically one last slide to say, comparison of these two models. In one, we learned good model parameters. In the other one, we kind of simulate a parallel algorithm. We don't really learn some model parameters. We simulate a parallel algorithm. And we can do this and we can make it work out. Each agent runs the transcript of its own actions in that parallel algorithm. So these were our results. Yeah, online with the sample. It's a sort of interesting model. And it sort of goes back to this sort of question that we've asked for a very long time. If yesterday's instance looks like today's instance, what can we do? Now, one way to do this is to sample from yesterday's instance and use it for today's instance. Then you're not overfitting to that. I'm saying if you sample from today's instance, you can do well on today's instance. And if the two are similar, then these samples should look close to each other. So I would like to say, what if I give you corrupted samples? Can you say something? I don't know much about that. There are various other problems I don't know how to solve in this model, but I'm going to stop here. And thank you. You know.
So if my weights are slightly more, I know that it's a point. Even that's when all happen, you see what proportional that is.
Yeah. In this case, I mean, in this, I mean, it's so robust, right? You know? Yeah, absolutely. So, but you know, so if you just try to do this via uniform convergence, there are still, you know, the weights you could learn fairly coarsely. They could be log m many values for each weight, but they are still log m to the m weights. So if you do that, then you still get a m log m in the additive term. And that's what we don't want to do. So somehow we are doing some smarter search within that and not just uniform convergence. Maybe there's another approach, but you know, but the naive approach will not work.
Any other quick questions? Yes, people ask questions.
Yeah. Cool.
Right.
Awesome.
Thanks, Anupam.
Thanks so much.